afternoon, everyone. So thank you for staying with us to the last section of today's forum. And our today afternoon sections are focused on hardware implementation related to the quantum communication and technology and applications. So also the two speakers from this section are also the PIs or co-PIs from our national team of the quantum program. So our first speaker for this section is Professor Ming-Chang M from Institute of Photonics Technology at National Tsinghua University. And Professor Li received his PhD degree in electrical engineering from UCLA in 2005. And before that, he used to be a supervisor at Phi in Taiwan semiconductor manufacturing company. And in 2005, upon his graduation, after receiving PhD degree, he joined the faculty of the Institute of Photonics Technology and the Department of Electrical Engineering at National Tsinghua University. Currently, he's a professor there, and during 2016 to 2019, he was the R&D director at the Intelligent Application Microsystem Division at Industrial Technology Research Institute in Taiwan for the developing of silicon photonics and optoelectronics devices. And his research institute include the photonic MEMS, including like linear or nonlinear silicon photonics, high-speed group 4 optoelectronics, microwave electronics, nano photonics, and integrated quantum optics, basically optics for the all spectrums. And he published over 100 journal paper and conference papers, including 2 invited book chapters, and holds 15 patents in Taiwan and also US. And he's now also a senior member of IEEE and Optical Society of America, and not to mention the program committees in several international technological conferences. And also, he received the National Tsinghua University Young Researcher Award in 2010, and also the 12th Far Eastern SU Science and Technology Paper Award, and the Young Optical Electronic Researcher Award in Taiwan. And he is now a PI of one of the national team focusing on the quantum the photonic chips. Okay, with that, time is yours, Professor Li.
Okay, thanks Junda give so detailed introduction to me. Okay, and also thank Ming-Xiu and also Ming-Xian and also Hong Hai company to invite me to give this talk. Okay, and so today I would just I will not focus on the quantum number generator. Actually, I propose in this Taiwan national team, but here I will more focus on the silicon photonics applied in the quantum photonics. Basically, just give you a very general picture on how to apply this technology in this quantum photonics. Okay, here. Okay, and so first I want to just give you some brief motivation why we are interested in the integrated quantum photonics. I think Yanhong already give some brief the motivation why we are interested in the quantum photonics. So you can see that if in the freeze optic we want to build a system, you need a lot of components to occupy all the optical table. And if we use this integrated photonic technology, then we can string all this system onto a chip. So for example, this is Xanadu. They just showed their quantum photonic processor. They on this chip, it's actually smaller than your fingertip, and it has a lot of components, including more than here is you can find this about 88 Alexander interferometer. Okay, so actually for this kind of the system, if we want to build on the other table, you occupy a lot of space, and to give a more detailed comparison to use free space optics and integrate photonics to implement quantum systems, I think use integrate optic has a lot of the advantage. So I just showed several key index about the system performance. In terms of loss, of course, free space optics actually have some advantage because all the components can be optimized, and we also can tune the condition. So free space have the advantage of the loss of the system, but for the other performance index, for example, nonlinearity, use integrate photonics actually have the advantage of the high optical confinement, so you can enhance this nonlinear effect. And also, it has a fast reconfigurability. Okay, so for example, on this optical table, right? If you drop something on this optical table, I think you must feel crazy. Okay, you will maybe need to spend 2 or 3 months to rebuild up the system. However, on this chip, even you drop on the ground, I think it's still workable. Okay, and also in terms of phase stability and scalability, I think use integrated optic approach it has a tremendous advantage on this. Okay, and so next, why we are interested in the silicon photonics? Actually, integrated optics, they have a lot of material systems, but here we are more focused on the silicon photonics. Actually, this is what my research interest. So why the silicon photonics? I think first, the silicon actually abundant on Earth. When I was an engineer in the TSMC, right, someone always suggests Morris to build a foundry for the 3.5. But at that time, I think they just said, that, okay, no, the substrate is too expensive. Okay, so you can find that the TSMC, although it is very strong in this fabrication technology, but it still stick to the silicon device. And also through this IC technology, we can leverage a very advanced fabrication technique, and also can share with some mature ecosystem for the state of our IC industry. So this is the reason why the silicon photonics receive a lot of attention. Okay, and so far I think silicon photonics already be applied in many applications. Okay, so from the long haul optical communication to the short reach optical communication, and to the sensor, and even applied in the military. Okay, so everything if you consider you can you need some optical system, then you can use this silicon photonic platform to implement this system. Okay, and so especially I think in Taiwan, I think we are very strong in the IC industry. Okay, and silicon photonics actually is also be included in the TSMC. So TSMC not only fabricate electronic devices, it also fabricate photonic devices. So this year they just announced they work with the NVIDIA and to develop this silicon photonics technology for their switching application in the server. Okay, and so far I think more than 10,000 optical components can be integrated on the single chip of the silicon photonics. Okay, so it's quite amazing. And we can for this scalability. So now I'm going to talk about, okay, so now since the silicon photonics already have a lot of application in the classical integrate optic systems. So how to apply it in the quantum photonics? Okay, and this picture actually is proposed by the Mark Thompson in University of Bristol in around 2016. Okay, so on this picture, it already shows some key component of the integrated of silicon quantum photonics. Okay, so at the first glance, if you are the silicon photonic guy like me, I would consider, oh, okay, so this technique actually is not quite difficult. Actually, if you are doing some classical silicon photonic components or device, so you will find that even more complicated device actually is what we are working on. But for the silicon, integrated silicon quantum photonics, you will find that most of them are made of a lot of the silicon waveguide and interferometer. But actually, when you really do this, develop this system, you will find that the spec we pursued are totally different. For the classical optics, especially for silicon photonics, for the classical optics, we are pursue the high speed. But here in the quantum photonics, we are pursued in the low loss photonics, and we deal with a very, very weak signal. Okay, so they're totally different, and actually it is in some sense even more challenging. And here I'll just quickly to summarize all the necessary key ingredient of the integrated quantum photonics platform. So in general, we need three components. So first is a photon generation, and the second is a photon operation, and the third is a photon detection. And the photon generation, we can find that you need a lot of this waveguide structure, including some ring resonator filter, and also the photon operation basically consists of a lot of the interferometer and some phase shifter. And next is a photon detection. It will need some superconducting narrow wire, single photon detector, or the image photodiode. And you also need some grading coupler to couple light from the fiber to the chip, or from the chip to the fiber. So in general, I think that the major difference, if you compare the classical silicon photonic and this integrated quantum photonics, for the classical silicon photonic, we are deal with the field, okay, the basic wave optics, okay. And for the quantum photonic, we are deal with a photon. And for the detection, in the classical photonics, we deal with the power detection. And here, but in the quantum photonic, we deal with the photon number detection. So they are the major difference. Okay, but because, as I mentioned, for the integrated quantum photonic, we deal with a very weak signal. And so we need all the components must be a very, very low loss. Okay, so first we talk about the photon generation. Okay, and here we are not talk too much about some quantum emitter, because usually quantum emitter you need to operate the system in the cryogenic temperature, and here we are more focused on the photon source, which can operate at room temperature. And to generate the photon source that operating at room temperature, we usually use the nonlinear effect to generate this photon pair. I think the previous speaker, they already introduced a lot of this for missing or the parametric down conversion to generate the photon source. So I think I can quickly just skip this cartoon. Okay. So, but anyway, I just want to emphasize that through this nonlinear effect, we can generate the photon source at room temperature. And through the integrated photonics platform, I think it has advantage of we can enhance this conversion efficiency, because of the higher optical confinement and more overlap between the signal and the idler. And also on the silicon photonic, because the silicon is invergent symmetric crystal, so it doesn't support the Pacos effect. So it only has a Curry effect. So for the silicon photonics, if you want to generate a photon pair, we usually to use the simultaneous forward mixing. Okay, and usually people they just use a very long waveguide, and because silicon photonics is is a high index, so we can, although we can make a very, very long waveguide, but we can to pattern this waveguide in this spiral shape, so we can still save the space on the chip. And so we can either use a very long waveguide to generate these photon pairs through the spontaneous forward mixing, or we can use the high Q microring cavity to generate this signal, either a photon pair. And so because all these components are integrated, so we can easily to scale up the photon source. And second, I think high Q ring resonator currently attract a lot of people to implement this quantum source. Okay, and because it will largely to increase the this generation rate and also the photon extinguishability. And but this photon pair generation is not deterministic, and for this integrated quantum source, we also need some high rejection rate pump filter to eliminate this the pump. Okay, and in terms of the total photon detection on the silicon photonic chip, and as we know that for most of the single photon detector, they are either can be implemented through this average photodiode configuration, or use the superconducting nanowire for this single photon detection. So we can implement this superconducting nanowire photon detector on the silicon photonic platform, and also can implement the silicon average photodiode on the silicon photonic platform. So you can find that. And the left, there's the people, they just do the wafer transfer to transfer niambien nitride to this silicon photonic waveguide. Okay, or you can directly to make a germanium on top of silicon waveguide to make this waveguide based single photon average diode. And but for the superconducting wire, then you need to operate in the cryogenic temperature. But for the germanium silicon spot, it can operate, still need to operate at a very low temperature. But for the silicon average photodiode, it can operate at the room temperature. But in terms of the detection efficiency, I think the superconducting wire still have the best detection efficiency. Okay, and the silicon actually is not too bad. It still can have a 70% detection efficiency. And for the but if you want to make this germanium on silicon average photodiode, and currently I think the high dark count rate and the detection efficiency still need to improve. But I think the technology actually is more and more. I mean, the epitaxial growth technology is more and more mature for this type of the component. I think the performance will keep increasing. Okay, so next, I think the major topic of my talk today, I think we're more focused on the photon operation on the silicon photonic chip. And I think I probably can quickly to skip out this figure. So basically, for the integrated photonics, we usually to use path encode photon to define a qubit state. So so here, right? If we just prepare two waveguide. So if the photon is appear in the bottom waveguide, then we can define this state 0. If it appear in the top waveguide, we define in the state S0 is 1. Okay. And there's some advantage using this path encoding. So because I think for the integrated photonic device, then I think the Mach-Zehnder interferometer is a very common in the integrated photonic device. And use this Mach-Zehnder interferometer, we can simply to change the state of the qubit. Okay, so this is from the classical field operation. This is a transfer function to define the input and output wave. And this quantum state, then the same, this transfer function we can use to change the input and photon cubic state. Okay, so here you can find that we use this tunable Mach-Zehnder interferometer. We can simply to implement a single cubic logic, quantum logic operation. So we can implement this Hadamard gate and poly XYZ just by tuning the phase of this tunable Mach-Zehnder interferometer. However, for the multi-cubic logic gate, it will be not that straightforward. Then it's need to rely on the measurement-based large-scale linear operator on the multiple photon to implement this multi-cubic logic gate. So, for example, this is the schematic of the control NOT gate for this two qubit. For this 2 qubit. Okay, so you can find that. So this cubic CNOT operation actually is through this waveguide mode interference. Okay, and then we can measure the output of the photon statistic at the output pole of this circuit. So in addition to the logic outcome, they also will generate some redundant outcomes. So that's so we need to use some ancillary photon state to post-select this logic outcomes. So this is usually the people that use passing code cubic to implement a multi-cubic logic gate. And so in previous year, we just try to try to develop a photonic waveguide and to implement this CNOT gate on a chip. So we use this silicon nitride waveguide as the main body of the photonics. And this silicon nitride waveguide, I think, have an advantage of the relatively low loss compared with the pure silicon waveguide. And the fiber to waveguide coupling loss actually is not is also can be is the moderate, is not introduce too much loss. And then we use a titanium nitride micro heater for this thermal optic phase tuning. Okay, and this is this device configuration actually is the similar, the same as the previous on the previous slide. So we just try to make this device and try to check try to test the function of this CNOT operation. Okay, and this is this fabricated device. So we can find that we can make a good device and only occupy a very small area. And then we just package this device. Okay, so finally we can fiber pigtail package it and operate this device. And we work with the Professor Chu and to test this device. Okay, and then so this is the result we get. So we just separate to show that we can have this CNOT function. And so first, the visibility of this single photon is around 85%. It's not bad. And also the fidelity is around 92%. And the more, I think there's also more some a report on this quantum information process on the silicon photonic platform from the quantum communication and the computing and to the simulation. So you can find that all this quantum information processing is based on this interferometer circuit. And here I just want to mention that so in order to make this interferometer circuit, then we need to wire control this interferometer circuit, the element on this interferometer circuit. So ideally, any arbitrary unitary operator can be implemented by the interferometer circuit, like showing on this two figure. And this two figure actually is made each node actually made a tunable beam splitter. So this beam splitter is made by the Mach-Zehnder interferometer. Okay, and then we can engineer the phase on each Mach-Zehnder interferometer to program this spin ratio and the phase of each beam splitter. But there are some technical challenges. First, we need an extreme low loss component, and we need to fast and efficient phase tuning. And another very important, we need to do the phase error correction. This is the most critical part of this quantum photonic circuit. So here, in my lab, we develop so this is just show you the inference of this phase error. Okay, so if there's some phase error here, then the original transfer function actually is not what you decide, and also the phase error is it actually is not cannot be predicted, and it will change by the temperature and some environmental effect. Okay, and so here we just develop we use the image resolve method to calibrate the phase error of the photonic circuit. So for example, so we will put some tapper here, so we can tap the waveguide power of the Mach-Zehnder interferometer. So this is a setup of we monitor the Mach-Zehnder interferometer. So we can do the large scale phase error correction. Okay, so we just tap at 5% of waveguide power, then we can monitor the condition of the each Mach-Zehnder interferometer or some key in the Mach-Zehnder interferometer. And then, so this will show you that we can use this approach to calibrate the phase error on the arm of the Mach-Zehnder or in the external phase. Okay, so we can find the maximum value and minimum value to calibrate all this phase error. And also, we also develop a very low loss silicon nitride waveguide. So basically, we just put a very thin silicon pad underneath the silicon nitride. And so you can find that the loss actually can be reduced from the previous 1 dB per centimeter to the 0.055 dB per centimeter. So this is around one more order magnitude smaller. And also through this structure, we can also implement a very high speed and high efficient phase tuning. So the left-hand feature, you find that's a conventional silicon nitride waveguide. So the heater need to far away from the silicon nitride. But using our approach, we can get this silicon step not only in the heater, but also part of the waveguide. So we can reduce the gap between the heater and the silicon nitride. So we can reduce the power consumption, and also the tuning will be much faster. So we can get around larger than 20 kilohertz tuning speed. So finally, I'll just give you a conclude my talk. So use the silicon photonic. I think that's some advantage. So first, we can leverage the advanced IC technology. So we can make a high quality of photonic components. And the second, I think maybe the most important is the technology supply actually is much mature compared with other material systems. So from the material design, fabrication, test, and the packaging, you can find the corresponding supplier. And also the scalability is also a very big advantage. But there's some challenge in the component technology. Okay, so first, the photon generation, we still need some deterministic, indistinguishable, and multiple room temperature photon generator. And also, we also need a large and high efficient low and also room temperature photon detection. And we also need a very high speed, the more than gigahertz, and low loss, low power consumption reconfigure circuit. Okay, so yeah, time's up and finished.
Good timing. Thank you very much for the nice talk. So we have time for a few questions from the audience in this room.
Can I ask what's the typical photon generation rate for the quantum source in the integrated photonics chips?
Okay, I think that sure there's a number here. I think depend on what kind of the component use. If the because actually the number is not and cannot. I just know that one is actually several order larger than the others. Okay, so you can find that there's some measurement result here. Okay, what? Okay, here. So you can find that that's a generation rate. So use a ring. then can go up to the tens of megahertz, the generation rate. Okay, and it's much faster than just a pure long silicon waveguide.
Okay, thank you very much. So I think due to time constraint, so we do have a few questions online, but maybe we can respond to that afterwards.
Okay.
And let's thank Professor Lee again.